Good morning students and welcome to today's class. We were discussing the chapter solutions and today we are going to start a new topic, that is Henry's law. Now, first of all, let us get to know what is this Henry's law. Okay, it's a law which states that, I'm writing the law, it states that mass of a gas, okay, states that mass of a gas dissolved in a given volume of liquid at a constant temperature is directly proportional, I'm writing in short, proportional, okay, to the pressure which is applied. Okay. In this law, it states that mass of a gas dissolved in a given volume of liquid at a constant temperature is directly proportional to the pressure which is applied. Now, mathematically, if we see, if M is the pressure, M is the mass of the gas dissolved in a given volume of liquid, and P is the pressure which is applied, then M is directly proportional to the P. Okay, that means the solubility of a gas in a liquid increases when more and more pressure is applied. Okay, when we apply more pressure, the mass of the gas which is dissolved in a liquid increases. But there is a condition. What is the condition? It must be a constant temperature. Okay. Now to understand this, let us take an example. Okay. I think we all have consumed these soft drinks or cold drinks, what we call it, right? When we open a cold drink, then what happens? A popping sound comes out, right? A hissing sound comes out. Okay. Now why such sound is produced? Because a gas is released on opening the seal or the cork of the bottle. What is that gas? That is carbon dioxide. Now we know that carbon dioxide is not easily soluble in water. Okay, but when high pressure is applied, what happens? Carbon dioxide becomes soluble in water. So when this carbon dioxide is made soluble in water, high pressure is applied, and that is why this carbon dioxide becomes soluble in water. But when we open the cork, what happens? The pressure decreases. Okay, the pressure decreases, and when the pressure decreases, this carbon dioxide gas, its solubility decreases and it comes out. Okay, it comes out of the liquid, and when it comes out, it makes a hissing or popping sound. Okay, so this is one of the examples of Henry's law. Once again, I am explaining Henry's law. What does it state? That the mass of a gas dissolved in a given volume of a liquid at a constant temperature is directly proportional to the pressure which is applied. The more pressure you apply to a gas, the more the gas will be soluble in that liquid. Okay? Is it clear? This is the mathematical statement. Now one more alternative statement is also there. Okay? Let us see what is the alternative statement. Henry's law can also be stated as the partial pressure of the gas in vapor phase, the partial pressure of the gas in vapor phase is directly proportional, I'm writing short, proportional to the mole fraction of the gas in solution. Okay, this is one more alternative statement of Henry's law. The partial pressure we know. Okay, it is the pressure exerted by a gas when it is present alone, right, in a container. The partial pressure of a gas in vapor phase is directly proportional to the mole fraction of the gas in solution. Okay, suppose we have a container here. There is a liquid, say, and gas molecules are dissolved in it. right? Gas molecules are dissolved in it. So these gas molecules will have exert a pressure. Okay. So what does the Henry's law state? That more and more gas molecules, the more the gas molecules are present in this liquid, more it will exert a, it will have vapor pressure. Okay. Or if it has more amount of gas molecules, the more will be its vapor pressure. This amount is expressed in terms of your mole fraction. Okay. So what is the mathematical statement of Henry's law? Alternative statement will say if P is the partial vapor pressure of the gas, that is directly proportional to the mole fraction of the gas. Okay, this is the mole fraction of the gas. The partial pressure of the gas is directly proportional to the mole fraction of the gas which is dissolved in solution. But again, it has to be at constant temperature. Okay, that's what that is, constant temperature. Now there is a proportionality sign. So if this sign has to be removed, then what we have to do? We have to introduce a constant, right? So the constant that we introduced here is your KH. Okay, this is a constant. KH is a constant and it has got a specific name. What is its name? It is called Henry's constant. Okay, Henry's constant. So this is the mathematical statement of Henry's law. Alright, P is equal to KH into mole fraction of the gas. Okay, here KH is the Henry's constant. Next we have characteristics of Henry's constant. Okay, I'm writing this one. Next we have characteristics of Henry's constant. Okay, so the first characteristics of this Henry's constant is that Henry's constant KH is a function of the nature of the gas. Okay, KH, that is Henry's constant, is a function of the nature of the gas. Now what do you mean by this? It means that KH, the value of KH depends upon the nature of the gas. Okay, different gases will have different values of KH. Okay, as we change the value, as we change the gas, the value of KH will also change. Okay, suppose we consider two gases, oxygen, and we consider another gas, suppose helium. Okay, so both are different gas, so both will have different value of KH. This is the first characteristic of Henry's constant. Okay, coming to the second characteristic, number two. Number two characteristic, what does it say? Greater the value of KH, lower will be the solubility of the gas. Okay, that means KH is inversely proportional to solubility. Okay, KH is inversely proportional to solubility provided at constant partial pressure and constant temperature. Okay, that means if a gas has more value of KH, the solubility of the gas will be low. Okay, suppose if we consider one example, say we have two gases, gas A and another one is a gas B. Okay, gas A has a value of Henry's constant, say 5. Okay, and gas B has a value of Henry's constant, say 10. So clearly gas B has higher value of Henry's constant, right? So out of these two, which will be more soluble? As we can see from this formula that KH is inversely proportional to solubility. That means higher the value of KH, lesser will be the solubility. Okay, so clearly gas B will have lesser solubility than gas A. Okay, gas A will be more soluble. So this will be the order. Gas A is more soluble than gas B. Why? Because gas A, the value of gas A has lower value of Henry's constant. Okay, gas A Henry's constant और value to जेहेतु कम हेतु करने यार solubility बेसी होगा. क्यों? Because KH Henry's constant is inversely proportional to solubility. ठीक है सर? KH जाने के KH or value যেনেকৈ বাঢ়িব solubility সিমানে কমিব. Okay, this is the second characteristic. Coming to the third characteristic, number 3 characteristic, that KH is directly proportional to temperature. Okay, KH is directly proportional to temperature. The more the value of the more is the temperature, the more will be the value of KH. Okay, so these are the characteristics of Henry's constant. Once again I am explaining. First is that Henry's constant is a function of the nature of the gas. Okay, what does this mean? This means that different values, different gases will have different values of Henry's constant. Second characteristic is that KH is inversely proportional to solubility. That means more the value of KH for a particular gas, lower will be the solubility. And number third characteristic is that KH is directly proportional to temperature. Okay, more is the value, more is the temperature, more will be the value of KH. That is Henry's constant. Okay. Next, we come to the applications of Henry's law. Okay, we have learned the law. What is this? And now we are going to discuss what are the applications. Okay, tar usefulness to key, tar applications to key Henry's life, Henry's law. Okay, so first, the application hai bahut simple example hai eta already kolo je ki hai, we consume cold drinks. Okay, am sobe cold drinks khao, soft drinks khao, tate ki hai carbon dioxide gas to high pressure tat soluble kora hoy. Okay, ene carbon dioxide easily soluble nohoy, but under high pressure it becomes soluble. Etu karone jetia ami bottle or jonto neck hoy ba seal hoy, when we open it, carbon dioxide gas comes out. Okay, as the pressure decreases. Okay, when we open the seal or the cork, the pressure decreases and the solubility of carbon dioxide gas decreases. Carbon dioxide etu karone ki hoy ulai ahe. Okay, solubility common karone etu ulai ahe. Jetia ulai ahe, it makes a hissing sound. Alright, this is the one of the example. Okay, cold drinks or hoy, you can also consider soft soda drinks. Soda drinks to etu same apply hoy. ঠিক আছে, যেতিয়া আমি বটলটো খুলি দিওঁ, then কি হয়, pressure decrease হয়, pressure decrease হোৱাৰ বাবে solubility decrease হয়, and etu easily carbon dioxide gas ulai ahe. Okay, it easily escapes out. One more example is application of this Henry's law is that the second application you can consider is that we know deep sea divers, right? Scuba divers. Okay, যেতিয়া scuba divers deep sea diving koribo jay, they take a gas of cylinder, oxygen cylinder with them, right, which is filled with oxygen for breathing purposes, of course. Now that oxygen gas, the oxygen cylinder mainly comprises of two gases. Okay, duta gas thake ki oxygen and nitrogen. Okay, duta gas thake primarily oxygen aru nitrogen. Etia when this deep sea diver, scuba diver, when they dive at the bottom of the sea, what happens? The pressure increases. Okay, as we know that as we go down the sea level, what happens? The pressure increases. Jimane ami tolole goi thakim ki hoy jabo, pressure to bahi goi thakibo. Okay, now according to Henry's law, what does Henry's law, what will happen? As the pressure increases, solubility also increases. Okay, Henry's law ki koy je jiman beshi pressure dia hobo eta gasor solubility eta liquid himane beshi bahi jabo. ঠিক আছে, তো যেতিয়া এটা স্কুবা ডাইভাৰে ডিপ সি ডাইভিং কৰে, কি হৈ যায়, at the bottom of the sea, what happens? The pressure increases, and pressure increase হোৱাৰ বাবে যোনটো গ্যাসৰ solubility হয় সেইটো বাঢ়ি যায়. Okay, so these gases are absorbed more in the blood. Okay, so deep sea diving যেতিয়া কৰে তেতিয়া কি হয়, solubility increase হৈ যায়. কিয়নো যেতিয়া bottom of the sea যায় তাত pressure to increase হৈ যায়. So pressure যেতিয়া increase হয়, these gases become more and more soluble in the blood. Okay, now oxygen gas is used for cellular purposes. Okay, বিভিন্ন কাৰণতে এটো oxygen gas আমাৰ বডিত এটো ইউটিলাইজ হৈ যায়. But this nitrogen কি হয়, this is unutilized. Okay, nitrogen is inert, এটো আমাৰ একো কামত নাহে. Okay, it is collected in the tissues কি হয় যায়, এটো collected হৈ যায়. Okay, now deep sea diving যেতিয়া কৰিলে তেতিয়াটো increase হৈ গ'ল solubility. Okay, these are absorbed, But when the scuba diver again comes to the surface, যেতিয়া আকৌ সাৰ্ফেচলৈ ঘূৰি আহে তেতিয়া কি হয় প্ৰেছাৰটো আকৌ ডিক্ৰিজ হয় ৰাইট প্ৰেছাৰটো ডিক্ৰিজ হোৱাৰ বাবে হেনৰিজ ল মতে কি হৈ যায় সলিবিলিটি ডিক্ৰিজ হয় okay solubility decrease হয় তো অক্সিজেনটো ইউজ আপ হৈ গ'ল but this nitrogen কি হয় it tries to escape out okay now when this nitrogen tries to escape out it forms bubbles in the capillaries okay আমাৰ যোনটো capillaries থাকে তাতে কি কৰে এইটো এটা বাবলৰ নিচিনা ফৰ্ম কৰে now this what happens because of the formation of the bubbles it restricts the blood flow okay blood flow to restrict কৰে and this leads to pain okay a medical condition which is known as your bends is a medical condition as well it gives rise to this condition okay and it is immensely painful for the scuba divers all right to resolve this problem it is a problem hoy ei problem to resolve koribole ki kora hoy oxygen jonto cylinder loa hoy along with oxygen and nitrogen one more gas is also taken that is helium okay helium gas to mix kori dia hoy yat all right beleg proportions ase okay I'm not going to that but along with oxygen and nitrogen helium gas is also being mixed with these two gases okay so what is the purpose of mixing helium or the solubility of that is very less okay the solubility of helium is very less so helium is not dissolved in not absorbed in the blood okay the blood or jeti absorb na hoy tetia a problem to create a hoy all right so what happens this is a direct application of your Henry's law all right so this is an important question and many questions related to this are asked in the examination all right application one more example or one more application of Henry's law is that at high altitudes what happens the partial pressure of oxygen is quite low okay so oxygen is inhaled very in less quantity and this leads to low concentration of oxygen in the blood okay oxygen or concentration blood or kome jay so the people living in there or the mountaineers okay the people who climb mountains what happens they inhale less amount of oxygen and the concentration of oxygen in the blood is also low so they are unable to think properly and this leads to another medical condition which is known as your anosmia okay anosmia so why this happens because at high altitudes the pressure is less and when pressure is less from Henry's law we know that the solubility decreases okay so less amount of oxygen is absorbed or soluble in the blood and that is why people living there or the climbers especially when they climb these high altitudes mountains then they are unable to think properly okay they develop confusion and this leads to a condition which is known as anosmia this is another example of or another application of Henry's law now we have discussed what is Henry's law its mathematical statement and what are the applications of Henry's law now let us discuss the limitations of Henry's law that is at which places this law fails to be applied okay where this law is not applicable so the first limitation is that this law that is Henry's law is applicable only to gases under ideal conditions okay is applicable to gases under ideal conditions okay now what do you mean by these ideal conditions ideal conditions mean that is under low pressure and at high temperature okay this law is applicable to gases under ideal conditions means low pressure under low pressure and at high temperature okay if we reverse the case if we consider that high pressure and low temperature this law will not be applicable okay coming to the second limitation the molecules of the gas should not dissociate associate in solution. Okay, I'm writing in short. The molecules of the gas in liquid should not dissociate. Dissociate means break down. It bhangi jabo na lage. Neither it should associate. Mane good khai jabo lage. Okay, it should not dissociate nor it should associate. Okay, jeneke agote asile teneke thakibo lage. Okay, this is another limitation. So the associate but dissociate hoy, Henry's law will not be applicable. Okay, this is to be kept in mind. Henry's law will not be applicable for those gases which associate or dissociate in solution. Alright, coming to the third limitation, that the gas should not react chemically with the solvent to form any compound. Okay, the gas should not react chemically with the salt to form any compound. That means junto gas we consider kori asu, okay, junto solvent it dissolve hoye ase, it should not react chemically. Okay, it should only be dissolved physically, but chemically eko reaction hobo na lage. Jodi chemically reaction hoy, Henry's law cannot be applied to the gas. Okay, for example, we take an example, ammonia, NH3. Okay, ammonia is a gas when this is dissolved in water. Okay, H2O. Then what happens? It forms NH4OH, ammonium hydroxide. Okay, it forms ammonium hydroxide. So it chemically react kori ase nohoy. This is reacting chemically, so we cannot apply Henry's law to this gas. Alright, Henry's law cannot be applied to this gas. Moreover, this ammonium hydroxide, being a weak base, also dissociates. Okay, it dissociates to give NH4 plus ion and OH minus ion. So here, duta condition hoye gise, eta chemically react kori ase, so applicable na hobo. Further, this ammonium hydroxide is dissociating. It bhangi porise into ammonium ion and hydroxide ion. So etu second condition to violate kori ase. That is why this is not, Henry's law is not applicable to this gas. Okay. Let us discuss again the limitations. Key limitations is first of all, this law, Henry's law, is applicable to gases only under ideal conditions. Ideal conditions means low pressure and at high temperature. Secondly, the molecules of the gas should not dissociate. Dissociate hobo na lagibo, but associate hobo na lagibo. Third limitation is that the gas should not react chemically with the solvent to form any compound. Gas to compound logot, solvent logot eku reaction hobo na lagibo to form any chemical compound. So if react kore, then Henry's law will not be applicable. Alright. Okay, now we have understood what is Henry's law. Now let us solve a numerical from NCERT. Okay, so here is a numerical. What does it say? If N2 gas, nitrogen gas, is bubbled through water at 293 Kelvin, how many millimoles of N2 gas would dissolve in 1 liter of water? Assume that N2 nitrogen exerts a partial pressure of 0.987 bar. Given that Henry's law constant for N2 at 293 Kelvin is 76.48 kilobar. Okay, so there is water. Okay, water is the solvent here. Water is it. Okay, this is water H2O. That ki kora hoise nitrogen of dissolve kora hoise. Okay, nitrogen is bubbled. That means it is made to be dissolved in water. Okay, nitrogen is made to be soluble in water. Okay, water kiman quantity loa hoise? It is 1 liter. 1 liter of water loa hoise. Okay, nitrogen gas is being dissolved at what temperature? 293 Kelvin temperature. Okay, so it is asked how many millimoles of nitrogen gas would be dissolved in 1 liter of water. Kiman millimoles of nitrogen gas dissolve hobo 1 liter of water. Okay, assuming that what dhori is that nitrogen gas exerts a partial pressure of 0.987 bar. Okay, nitrogen or partial pressure kiman dhara hoise 0.987 bar. Given that Henry's law constant for nitrogen is 76.48 kilobar. Iman here Henry's constant or value or nitrogen or value. Okay, so let us solve this numerical. given কি আছে আমি এটো লিখি লওঁ so given কি হয় এটো আমি লিখি লওঁ given কি আছে here nitrogen or partial pressure what is the partial pressure of nitrogen here it is how much 0.987 bar right 987 bar 0.987 bar is the partial pressure of nitrogen then kh of value here আছে and is constant this is its value 76.48 kilobar okay so kilobar আছে এটা bar আছে we can change its unit to bar so if we change to bar it will be 76.48 into 10 to the power 3 bar okay for converting this has to be converted to the same unit one is in bar another one is in kilobar so it has to be converted into the same unit so for converting kilobar into bar we will multiply 10 to the power 3 okay and this is getting converted into bar this will get converted into bar alright then what else is given volume of water is 1 liter right and we are supplied with temperature is 293 Kelvin okay always write what are the data given in the question okay it will help to it will be easier for you to solve the question bank alright so these are the things that are given and now we have to find out how many millimoles of nitrogen will be soluble in water okay so these things are given so we can apply Henry's law here so what is Henry's law from Henry's law okay from Henry's law what we can say partial pressure of nitrogen is equal to kh Henry's constant into mole fraction of nitrogen isn't it this is Henry's law partial pressure of nitrogen is equal to kh Henry's constant multiplied by mole fraction of nitrogen okay so you are supplied with Henry's constant and partial pressure from this we can easily calculate the mole fraction of nitrogen so keeping mole fraction to this side if we bring this one alright we have kept mole fraction of nitrogen to other side one side and we have brought kh to this side okay cross multiplication now this is given partial pressure of nitrogen is given how much it is 0.987 bar and the value of kh is 76.48 into 10 to the power 3 okay right now if we solve this on solving this I'm writing directly here we will get 1.29 into 10 to the power minus 5 okay this would be the value of mole fraction it will have no unit as we know that mole fraction does not have any unit okay so this is the value of mole fraction of nitrogen which is dissolved in 1 liter of water but we are not asked to find mole fraction right we are asked how many millimoles of nitrogen will be soluble so from this we have to find out the number of millimoles okay so how can we find out in this part we have found out this one mole fraction of nitrogen was 1.29 multiplied by 10 to the power minus 5 alright now from here we have to find out the number of millimoles of nitrogen that is dissolved okay so to find out that one we have to remember the definition of mole fraction okay so what is the definition of mole fraction means the number of moles of one component divided by number of moles of all the components present in a solution alright number of moles of one component divided by number of moles of all the components present in the solution now in this particular case we have got a binary solution right binary solution means solution containing two components only two components are present here what are they nitrogen and H2 water right these are the two components that are present in the solution alright so if we write the formula of this one okay mole fraction of nitrogen but we can say by definition number of moles of nitrogen divided by number of moles of nitrogen plus number of moles of H2O right this would be the formula because only two components are there So at the denominator only number of moles of nitrogen plus number of moles of H2O water will be there. Okay, but you see here nitrogen is soluble, is very less soluble in water. Okay, the solubility of nitrogen is very less in water. So the number of moles of nitrogen will also be less, right? As nitrogen is very less soluble in water, the value of number of moles of nitrogen that is soluble in water will also be very less. Okay, so as in comparison to this one, this value can be neglected. Alright, whenever we are to compare, when we are to add two values, the value which is smaller than the very small than the other can be neglected. For example, if I write 1 plus 0.00001, this is equal to 1.00001, right? If we neglect this one, this is approximately equal to 1. You can also neglect this one. Why? Because this is very less as compared to 1. So here also the value of this one, number of moles of nitrogen, is very less as compared to the value of this one. So we can neglect this value. Alright. So here I am writing as nitrogen is very less soluble in water, so number of moles of nitrogen will be very less than number of moles of H2O. So this factor, number of moles of nitrogen, can be neglected. Okay, this factor can be neglected. So if we neglect this factor, what will be the equation? This one. This will be our equation, resulting equation, right? If we neglect this factor, then this will be the resulting equation. Now it has become very simple. Okay, you can solve this problem without neglecting also, but the calculations will be tedious. Okay, calculations to all of one difficult over. So to simplify it, we have neglected this term. Okay, now we put the values and just we solve it. Okay. One more thing, number of moles of, we have to calculate the number of moles of water also. Alright, so always remember here 1 liter of water is being taken and 1 liter of pure water contains 55.55 moles of water. Okay, remember this one. So this value we have already calculated. How much? It is 1.29 into 10 to the power minus 5 equal to number of moles of nitrogen, and this value, as I already told you, this will be 55.55. Now, if you cross multiply this, then number of moles of N2 will be 1.29 into 10 to the power minus 5 multiplied by 55.55. Okay. Now, if we solve this, on solving this, the value is 7.16 into 10 to the power minus 4. Okay, this is mole. Okay, MOL, mole. This is the unit. Okay, 7.16 into 10 to the power minus 4. But you are not asked to find out the mole. You are asked to find out the number of millimoles. Okay, so from moles we have to convert it into millimole. Alright. Now how we will convert from moles to millimoles? Say from if we convert 1 liter to milliliter, what do? We multiply a factor of 1000 or 10 to the power 3. So here also we are going to do the same thing. If we multiply this one, if we want to convert moles into millimoles, we have to multiply by a factor 10 to the power 3. Okay, so let us multiply this one, 7.16 into 10 to the power minus 4 into 10 to the power 3. Then this will get converted into millimoles. Okay, millimole. So if we simplify this one, it will be 7.16 into 10 to the power minus 1 millimole, right? Or we can also write it 0.716 millimole. Alright, so this is our 0.716 millimole. This number of millimoles of N2 nitrogen will be dissolved in 1 liter of H2. Okay, so I hope this topic is clear to you. So that's all for today's class. We will take another topic. We will continue another topic in the next class. Okay, so that's all for today. Thank you, students, and have a nice day.